we're going to talk about some exponent rules. So we're going to talk about where they come from and then how to use the rules themselves, which we can kind of treat like shortcuts. If you ever get stuck though, you can always write out your exponents to see what's going on. So if we look at this first example, we have 6 squared times 6 to the 9th power. The rule tells us that when we're multiplying numbers with the same base, in this case 6 is the base, we keep the base the same and add the exponents. So you can see we kept the base 6 and then we added those exponents. So 2 and 9 were added to give us that answer 6 to the 11th power. If you weren't quite sure or you forgot the rule, you could write it out using our definition of exponents. 6 squared, we know, means 6 times 6. We multiply the base by itself twice. Then 6 to the 9th tells us that we need 9 more 6s. And as you can see, if we count them out, that gives us 11 total 6s, which gives us our answer 6 to the 11th power. If we look at this example, 7 to the 3rd times 7 squared. If I use that rule, I know the base 7 is going to stay the same, and I would add the exponents. So I end up with 7 to the 5th power. If I wasn't sure of that rule, I could write that 7 to the 3rd times 7 squared. 7 to the 3rd power is 7 times 7 times 7. 7 squared is 7 times 7. If I count them out, there's 1, 2, 3, 4, 5 7s. So I know that also gives me 7 to the 5th power. Now, if we look at this next one where we have a power to a power, we have 6 squared raised to the 9th power. When we see those parentheses, it usually means multiply. So when there's an exponent next to the parentheses, we keep the base the same, and multiply the exponents. So we'd have 6 to the power of 2 times 9, or 6 to the 18th. Right, remember, this is telling us inside we have 6 squared, so that's where we're getting this 6 times 6 from. And then this exponent of 9 is telling us we need it 9 times. So if we write it out, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 6s, which gives us that 6 to the 18th power. If we look at another example, we have 7 to the 3rd power squared. So I know for that shortcut using the rule, I'm going to multiply the exponents. So I'll really have 7 to the power of 3 times 2, which gives me 7 to the 6th power. If I wasn't sure about this rule, I could write it out. I know that I have 7 to the 3rd power, so that's 7 times 7 times 7. And that exponent of 2 is telling me I need to write it twice. So I have 7 times 7 times 7 again. If I count them up, I have 6 7s. So I know that's the same thing as 7 to the 6th power. Now, if we look at our rule for division, we have the example 5 to the 9th power divided by 5 to the 3rd power. So when we're dividing numbers with the same base, we keep the base the same and we subtract the exponents. We always do the exponent in the top minus the exponent in the bottom. So in this case, we'd have 5 to the power of 9 minus 3, which gives us our answer of 5 to the 6th power. If we weren't sure, we could write it out. So 5 to the 9th power tells us we need 5 times itself 9 times, which is up in this numerator. And 5 to the 3rd power tells us we need 3 5s in the denominators. Then we can cancel out. So we can cancel out 3 5s on the top with 3 5s in the bottom. If we count what's left over, we have 1, 2, 3, 4, 5, 6 5s left over, which gives us 5 to the 6th power. So if we look at another example, 3 to the power of 8 divided by 3 to the power of 5. If I use that shortcut, my base 3 stays the same. I do the top exponent minus the bottom exponent, which gives me 3 to the 3rd power. If I wasn't sure of the rule, I could write it out. I'd have 3 times 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 3. Let me double check. I've got 1, 2, 3, 4, 5, 6, 7, 8 3s. And I need to divide by 3 to the 5th power, so I need 5 3s. 1, 2, 3, 4, 5. I can cancel out a 3 in the numerator with a 3 in the denominator, and I'm left with 3 3s, so 3 to the 3rd power. Now, if we look at one that's a little weird, we have 2 to the 4th divided by 2 to the 6th. The base 2 stays the same. I do the top exponent minus the bottom exponent, and I end up with 2 to the negative 2nd power. But that looks kind of weird. We haven't seen negative exponents before. So let's use the when in doubt, write it out theory to see what really happens. If we look at that 2 to the 4th, that's telling me I need 4 2's in my numerator. And that 2 to the 6th is in the denominator, so I need 6 2's in the denominator. Now if I cancel, I'm left with these 2 2's in the denominator. So I know I have 2 squared in the denominator, and in fractions when everything cancels out, I have 1 left. So that means that what we got using that first method, that 2 to the power of negative 2, is the same thing as what we got using that second method, the 1 over 2 squared. And when we're dealing with exponents, we actually never want to have negative exponents in our final answer. So that answer, 1 over 2 squared, is going to be our final answer. Now, let's talk a little bit more about those negative and 0 exponents. Let's try to find a pattern if we focus on our powers of 3. So if we have 3 to the 3rd power, we know that's 3 times 3 times 3, which gives us 27. If I have 3 squared, I know that's 3 times 3, which gives me 9. If I have 3 to the 1st power, that's just telling me to write 3 once, so it's the same thing as 3. So if I'm trying to figure out what 3 to the 0th power is, I need to find a pattern going down. So to get from 27 to 9, I can divide by 3. And that pattern works again to get from 9 to 3. So I'm going to follow that same process. I'm going to divide by 3. And if I do 3 divided by 3, that gives me 1. So if we have anything except 0 raised to the 0th power, is going to give us 1. As the answer. So if we had something like 2 to the 0th power, it would be 1. Even if we had a variable like x to the 0th power, it would give us 1. If we had a negative number like negative 3 to the 0th power, it would give us 1. But if we had 0 to the 0th power, we'd say that one is undefined. Now, if we keep going to try to figure out our negative exponents, I'd have 3 to the negative first power. Well, following this pattern, I need to divide by 3 again. So I'm going to take that 1, my answer from the last example, and divide by 3. So I end up with 1/3. If I think about 3 to the negative second power, I would need to divide by 3 again to continue that pattern. If I divide 1/3 by 3, that gives me 1/9. And hey, I know 9 is just another way to write 3 squared. And if we double check one more time, 3 to the negative third, if I divide by 3 again, I'm going to end up with 1/27. And I know 27 is the same thing as 3 to the third. So that negative exponent tell us to move. That whole power. So if I had something like 4 to the negative second, that's telling me to move that to the denominator and make the exponent positive. So let's look at a few examples with these negatives. If I have a to the negative 8th power, I know I need to get rid of that negative 8, assuming my directions are telling me simplify, because I never want a negative exponent in my final answer. So I can think of it as that a to the negative 8th power being up in that numerator. A negative exponent tells me to move it, so I need to move to the denominator and make the exponent positive. When there's nothing left in a spot for a fraction, I put a 1 up there. So my answer is 1/a to the 8th. If I look at this next one to the right, 1 divided by b to the negative 3rd power, we just said that negative exponents tell us to move. So right now it's in the denominator. I need to move it up to the numerator. When I move a negative exponent, it becomes positive. So I have b to the 3rd power over 1, which I know is really just b to the 3rd power. If we look at the next example, 5 times d to the negative 6th. Now this d has a negative exponent attached to it. The issue is that 5 does not. I'm going to backtrack. Remember when we had just 3 to the 1st power? We said that was the same thing as 3. So here this 5 is the same thing as 5 to the 1st power. So because the 5 has a positive exponent attached to it, the 5 is going to stay where it is up in the numerator. Because the d has a negative exponent attached to it, it needs to move to the denominator to become a positive exponent. So our final answer is 5/d to the 6th power. If we look at this next example, c to the negative 4th divided by c squared, there's actually 2 different ways to deal with this problem. I could use that division rule first. So I know if I'm using the division rule, I need to subtract my exponents. So I'll c to the negative 4th minus 2. That gives me c to the negative 6th power. But I know I can't have negative exponents in my final answer. So I'm going to move that c to the denominator, make the exponent positive, and put a 1 in that numerator to get my final answer of 1/c to the 6th power. The other way to deal with this problem would be to get rid of that negative exponent first. So I could have said I have c to the negative 4th. I need to move it to the denominator and make it a positive exponent. C squared is already a positive exponent, so it's going to stay where it is. And when everything cancels out in a fraction, I'm just left with 1. Now I need to continue simplifying because I have that base c written twice. So in the denominator, I have c to the fourth times c squared. When I multiply, I know I add the exponents. So the denominator is going to give me c to the sixth. And that 1 stays the same up in the numerator. If I look at another example, we have e to the fourth power raised to the negative third power. We know that when we have a power raised to a power, we really multiply the exponents. So that gives me e to the negative 12th power. I need to get rid of that negative exponent, so I move to the denominator and make the exponent positive. There's nothing left in the numerator, so I fill in a 1 to get my final answer of 1 over e to the 12th. In the next example, I have 5 times f to the 6th power raised to the power of negative 2. Now, just like we did before, when I have that coefficient of 5, I'm going to write in an exponent of 1 to remind myself that that exponent is there. Then I'm going to take this negative 2, and I need to multiply it with all of the exponents inside the parentheses. So that's going to give me 5 to the negative 2nd power times f to the negative 12th power. Now I need to get rid of both of those negative exponents. The negative exponents tell me they need to move to the denominator, so I'll have 5 squared times f to the 12th. There's nothing left in the numerator, so I put a 1, and I get my final answer, 1 over 5 squared times f to the 12th.